Hello. Today I'll try to explain time dilation, why time appears to be passing slower for people moving very quickly relative to you. Now, some of the key ideas is the way I look at it, special relativity is how things appear to you if they're moving very fast relative to you. Now, unless you actually come to the same velocity and are going along together, you can't really compare notes. And what makes the time dilation actually happen once you've done that depends on who's been doing the acceleration. If you read through my notes and saw the whole equivalence principle with general relativity, if you're in a big gravity field or if you undergo a large acceleration, time actually slows down. Like if you are right by a black hole, time will slow down ridiculously depending on how close you're getting, because you're undergoing crazy accelerations or you're in a big gravity field and the two situations are equivalent. But for special relativity, instead of general relativity, you're just basically saying how things look, how things appear to you if they're moving very fast relative to you. So knowing that, a lot of this stuff won't make a ton of sense because the secret is that what appears to be a time passing for one observer is movement in time and space relative to another. So one person will think like, oh, that person just stayed still and time passed. And the other person will be like, oh no, this person was moving and time passed, like a combination of it. So this is the whole idea of space-time. So keeping all that in mind and the fact that this may not make immediate sense until you get really into Minkowski diagrams, space-time diagrams, which I will make an optional activity at the end of the week. Let's start with the idea of a light clock. So the idea of a light clock is, from your perspective, if you're on the Earth, if you are in a spaceship moving very quickly relative to the Earth, from your perspective, light is just going up, hitting a mirror and bouncing back down, getting detected. It doesn't take that long because it only traversed 2h as distance. Whereas if you're on the Earth and watching that exact same light ray move, it traveled significantly further. Though this is horribly skewed because this would imply that the spaceship is traveling faster than the speed of light because L is so much bigger than h. But regardless, you get the idea. Anyway, so someone on Earth thinks the light traveled this path, and so since this guy thinks not much time passed because the light only went 2h, and this guy thinks more time passed because 2d passed, from that you can calculate your time dilation formula, how much slower this guy will appear to be moving from the perspective of this guy. So t is the time of the event measured by the observer that's moving relative to the event. So usually we've got Earth and a spaceship or something. Though keep in mind, it does work the other way around too. It will appear to, if you're on a spaceship and moving really fast, people on the Earth will also appear to be moving slowly as well until you accelerate, like to come back. Anyway. So that's the gist. T is time measured by the observer that's moving. Usually that's the person on the planet or whatever. And T naught is the time for the person moving relative to you, is how I think of it. So we end up with our formula. This lovely guy. If I can zoom in. There we are. So sorry, my thing froze. There we are. So this is the time usually of someone in a spacecraft, but who's ever moving relative to you, how much time will appear to be passing for them. This is the square root of 1 minus their velocity squared divided by the speed of light squared. Speed of light squared is always 3 times 10 to the 8 meters per second squared. So you just do this. Notice v can't be greater than c, or we've got the square root of a negative number, and that's trouble. Also, we won't be getting a huge effect unless v is actually quite close to c. So anyway, the time that passes from your perspective on Earth is equal to the time you, from your perspective, passed for the person on the spaceship, if you're watching a clock on the spaceship or whatever, divided by the square root of 1 minus v squared over c squared. I'll do 2 questions and then try and leave it, even though I will definitely be going above the recommended length of videos. But it's relativity, so what you gonna do? All right, so here's a basic question, number 2 here. We got some astronaut traveling at a constant speed of 7.5 times 10 to the 7 meters per second through space relative to Earth. And according to timing devices aboard the space vehicle, the travel lasted 3 years. How long would you think the trip lasted? So you're going and looking at the spaceship through your telescope and you're watching their clock. You saw 3 years passed. From your perspective, your t would equal 3 years divided by 1 minus 7.5 times 10 to the 7, which is getting like pretty darn close to the speed of light. It's like a quarter of the speed of light divided by c squared. I might just call this a quarter c. So if this is a quarter of the speed of light, then that would be equal to 3 over root 1 minus 1/4 c all squared over c squared. So it's equal to 3 over, basically 1 over 1/16. So it's square root of like 15 over 16. So it'll be a bit longer. Notice not like wildly longer. I checked the answer key to see what, but even though you're going a quarter to the speed of light, it's not incredibly different. It starts to get incredibly different once you are at like 90% of the speed of light, or 98, 99, but you got all sorts of other crazy stuff going around that point. Like relativistic mass, you have to add more and more energy to have the same change in velocity. It gets pretty ridiculous. Anyway, so that's that guy, pretty straightforward. Here's the amount of time passing relative to the spaceship. You're using your telescope and seeing kind of how their clocks seem to have said from your perspective, how long has passed, and then 1 minus v squared over c squared. And if you've got the ratio of c, it's easier because you can cancel out the c squareds. Yeah, it's basically 1 minus 1/16 is what this ends up being. And that's why I ended up with this, because 1 minus 1/16 is 15 over 16. All right, and the last one I'm going to do is this sucker, which requires this sort of setup. So you're traveling through space at a constant speed of this relative to Earth. Your friend who stayed back on Earth aged 35 years during the trip. How many years did you age? So I'm just going to do 6 here. So you're in the spaceship, you aged 10 years, and your friend aged 18 years. How fast was your space vehicle traveling through space relative to Earth? By the way, you would not get this from your perspective unless you came back and noticed the difference. So it's a little funny that way. Real things happen during the acceleration. Aside from that, it's sort of perspective. All right. So in this case, our formula is t equals t naught over root 1 minus v squared over c squared. We know t is 18. We know t naught is 10. You're the guy in the spaceship moving. And and that's going to equal 1 minus v squared over c squared. So what we probably do is kick this guy up top and kick this guy down there. So we would end up with 1 minus v squared over c squared equals 10 over 18, and then I will square this. I took this guy out of the square root by squaring both sides. So I kicked the 18 down and squared both sides. Then at that point, we could do 1 minus 10 squared over 18 squared equals v squared over c squared. And basically, we can kick this, multiply both sides by c squared, and then take the square root. So we'd have c squared 1 minus 10 squared over 18 squared equals v squared. And then if we square root both sides, we would end up with v equals c root 1 minus 10 squared over 18 squared. Sort of an interesting formula if you think about it. And this would always be the way to solve for the relative velocity based on the different perspectives on time passing. It would always be v equals c root 1 minus your TO squared over t squared. So if you happen to remember it, you can always use that. It's the same thing, we just rearranged. All right, that is plenty for today. Good luck with this. You do have the answers, which I've boosted to the top of the Google Classroom. Good luck, and have a great rest of your day.